Welcome to lecture 44 of the open course on diffusion in multi-component solids. In this lecture, I will talk about interdiffusion analysis of multi-component diffusion couples. I would first demonstrate how interdiffusion fluxes can be determined from experimental concentration profiles in a multi-component diffusion couple with some examples. Then I will introduce you to the concepts of zero flux planes and uphill diffusion, and would like to highlight the significance of diffusional interactions in the context of ZFPs and uphill diffusion. The last class we talked about interdiffusion analysis in binary systems. Today we will study interdiffusion analysis in multi-component systems. So, for example, let us consider a ternary diffusion couple. Let us say on left side we have an alloy 50 copper, 30 nickel, 20 zinc, and right side we have pure copper, that is 100% copper. So, this is my C copper minus the left terminal alloy concentration of copper. This will be C copper plus. For nickel, say this is C nickel minus, this would be C nickel plus, because C nickel plus is 0 in the right terminal alloy, and this is C zinc minus, this is C zinc plus, which is also 0 in the right terminal alloy. Since we are dealing with ternary diffusion couple, we have two independent fluxes. So, if we write for copper, if we take zinc as dependent component, we have J tilde copper as minus D copper tilde zinc dou C copper by dou X minus D tilde copper nickel zinc dou C nickel by dou X and J nickel tilde equal to minus D tilde zinc D nickel copper dou C copper by dou X minus D nickel zinc dou C nickel by dou X. So, we need 4 interdiffusion coefficients at any given composition of the ternary systems, 1, 2, 3, 4. How do we find this? For binary, we use the formula D tilde equal to minus 1 by 2 T integral x minus x naught dc divided by dc by dx. So, if we compare with Fick's law, this straight away tells me that the numerator is nothing but the interdiffusion flux, but this is for binary system that we had derived. How do we go about finding interdiffusion coefficients in ternary? Because if we apply the continuity equation, it is not as simple as for binary, because now it is a coupled equation. So, if we consider in general components 1, 2, 3, we can write D11 tilde 3 dou C1 by dou X plus D12 tilde 3 dou C2 by dou X. So, in order to go ahead, we will use a very powerful approach which was proposed by Dayananda. With this approach, we first find out the interdiffusion flux directly from the concentration profile that develops in the diffusion couple at the end of the diffusion annealing. So, let us see how do we go about this. We know the continuity equation dou C by dou T at x should be equal to negative of dou J tilde by dou x at T. For ternary, we have two independent concentration variables. So, we need to mention at least two concentrations in order to completely define a composition. So, we would like to denote this with subscript I, C I and J I tilde. Again, we would like to use the Boltzmann parameter here, or lambda, which is equal to x over root T. We assume that each composition plane that develops in a multi-component diffusion zone is also a function of lambda, and this has been shown to be true in many of the ternary diffusion couples experimentally. So, lambda is equal to x over root T, and so we have dou lambda by dou x is equal to 1 over root T and dou lambda by dou T is equal to minus x over 2 T root T. If we look at the left hand side, in the thermodynamics refresher, we had seen the upstairs, downstairs, inside out formula for the partial derivatives, which we can apply here. So, we can write with that formula dou C I by dou T at x times dou T by dou x at constant C I times dou x by dou C I at T should be equal to minus 1. So, we get dou C I by dou T at x equal to negative dou x by dou T of C I times dou C I by dou x at T. Now, if you look at the first term on the right hand side, dou x by dou T at constant C I, this is nothing but the velocity of the composition plane C I. So, we can write dou C I by dou T at constant x is equal to V of C I, there is a negative sign here, times dou C I by dou x at constant x. Now, let us try to find out this V of C I. V of C I is dou x by dou T for C I, and since C I is a function of lambda, we can write this as dou x by dou T at given lambda. And now, lambda is equal to x over root T. So, we can write x as lambda root T, and so dou x by dou T at given lambda, since lambda is constant, we just need to differentiate root T, and that should be equal to lambda over 2 root T, and if we substitute again for lambda, this is nothing but x over 2T. So, V of C I is given as x over 2T, and if x naught is our origin, we can write it as x minus x naught over 2T. If we substitute back into this equation here, and then if we go back to the continuity equation, we get minus x over 2T times dou C I by dou x should be at constant constant T. From here it should be at constant T, should be equal to minus dou J I tilde by dou x at constant T. Since the partial derivatives on both sides are at constant T, we can take those out, and if we multiply it by dx on both sides, we get minus x over 2t dci should be equal to d J I tilde. There is minus sign on both sides, so it will get cancelled. Now, if we integrate both sides from the left terminal to the desired x, we get J I tilde at x equal to minus infinity to J I tilde at x should be equal to integral Ci at minus infinity is Ci minus to Ci at x, and we are considering the fixed annealing time. So, we can take this t out here, x dci, and more appropriately if we use x naught as our reference plane, this should be equal to x minus x naught dci. Now, we know on the two terminals the diffusants will never penetrate, and so the fluxes at the two terminals would be 0. So, at the left terminal, that x equal to minus infinity, J I tilde is 0. So, we straight away get J I tilde at x should be equal to 1 over 2 t integral Ci minus to Ci at x, x minus x naught dci, and this is how we can get the formula for interdiffusion flux. So, we can obtain interdiffusion flux directly from the experimental concentration profile. So, I will illustrate how. So, consider any one of the profiles that developed after the diffusion annealing, let us say component I. So, Ci minus is again left terminal alloy concentration, Ci plus is the right terminal alloy concentration. If we want to evaluate the interdiffusion flux at any position x, we use that formula, and here this integral is nothing but again the area under the curve. So, this integral here would be this area. This is my metanoplane x naught here, and this is the integral x minus x naught dci from Ci minus to Ci at x. So, just by finding the area under the curve and dividing it by 2t, we can get the flux at any position x. We derived this formula again independent of the number of composition. So, this should be applicable to a multi-component diffusion couple. This way, we can obtain the interdiffusion flux of each component that at every composition plane that is developed within the diffusion zone here. Now, let us try to look at the nature of the diffusion flux profiles that can be obtained. So, consider again this concentration profile of component I, which is developed in the diffusion zone after the diffusion annealing time t, and we want to determine the interdiffusion flux, and we want to see the nature of diffusion flux profile in the diffusion zone. We derived the formula for J as Ji tilde at x is equal to 1 over 2 t integral Ci minus to Ci x minus x naught dCi. So, if we consider any location, let us say A here, and this flux will be 1 over 2 t times the area under the curve. So, this will be the area that we need to determine. So, let us call this area A, B, C, D here, and this the sign of the flux would be, since x minus x naught on left side is negative and dCi, Ci is decreasing with x. So, dCi would be negative, and so the sign of the flux would be positive. So, the flux at A would be positive. So, we know Ji tilde at A would be area A, B, C, D, A, and this would be positive. If we determine flux on the left side of metanoplane, but at a different location, let us say E here, then we need to consider this area AEFC, which is again positive and greater than the area ABCD. So, the interdiffusion flux will be higher at point E than at A, and we can see the interdiffusion flux is positive and it is increasing with x until we reach this position of metanoplane x naught. Now, what happens beyond x naught? If we consider any position, let us call this as G here. So, for this Ji tilde at G would be 1 over 2 t times, we first need to integrate up to x naught. So, the area would be A D C, let us call this as H, this as K. So, the first integral would be DHC, which is positive. Next, the integral from x naught to point G, that would be area HGK. So, this will be area DCHD and area HGK H. This has a positive sign, but now beyond x naught, x minus x naught is now positive, but DC is still negative, and so this area will have a negative sign attached with it, and we can see beyond the metanoplane the flux starts decreasing, and until in the terminal it will again reach 0, and this is how the interdiffusion flux profile will look in the diffusion zone. At the two terminal ends, the fluxes would be 0. That is because we are dealing with infinite diffusion couples. The infinite boundary conditions are maintained, and the flux will have a maximum at the metanoplane location. Similarly, if we are dealing with a concentration profile which has opposite gradient, a positive gradient, logically the interdiffusion flux will be negative. With the similar logic, we can show there will be a minimum in the interdiffusion flux at the metanoplane location. Okay. Now, this is when we are considering the normal concentration profile like this, but in multi component systems many times there will be maximum and minimum developed on the concentration profiles. So, how do we get the interdiffusion fluxes in that case, and what special features it develops? Let us try to look at it. So, let us consider another concentration profile, and as shown here there is a maximum developed on this concentration profile here. So, what would be the nature of interdiffusion flux profile here? Let us try to assess that. Up to the point of maximum, that is up to point B here, we know the interdiffusion flux would be negative, because x minus x naught, based on this formula, x minus x naught is negative, but dCi from A to B is positive, and so the flux would be negative up to point E. In the terminal, of course, the flux is 0 and it is increasing in the negative direction to point B. What happens at point B? Beyond point B, now the slope of the profile has changed. Here dC is now negative, and so any additional area contribution would be positive, and so the magnitude of flux will start decreasing beyond point B, or beyond the maximum on this profile here. So, if you want to find the flux at a point D, for example, so that we can find as Ji tilde at D. We can split that integral at the point of maximum. So, it will be Ci minus to Ci at B x minus x naught dCi plus integral Ci at B to Ci at D x minus x naught dCi. Of course, this has to be multiplied by 1 over 2t. Now, this integral, the first integral here, is nothing but this area A B G E A, and it has a negative value. So, this is area A B G E A, and the integral Ci integral from Ci at B to Ci at D will be the area B G F D, and it will have a positive value. So, area B G F D B times 1 over 2 t. So, this area minus this area, there is a common area B G E C here, that will be gone, and so we have this area C E F D C minus area A B C A. So, this will be the value of flux at D, and since these two have different signs, we see that after maximum the interdiffusion flux starts decreasing in magnitude here. Now, what if the two areas are equal? So, this area is equal to this area. then obviously the flux at point D here would be 0 if area CEFDC equal to area ABCA. This is point D here. Beyond this, the magnitude of the positive area would increase, and so the flux will become positive, and it will keep increasing in the positive direction until the metanoplane position, and the beyond metanoplane position again the flux will start decreasing until it becomes 0 in the terminals. And this is an interesting profile. It has a special feature in the interdiffusion flux profile. You can see in this particular case the flux is actually going to 0 within the diffusion zone, and this is called 0 flux plane for component I. And these ZFPs are special features because they indicate there exist strong diffusional interactions. The existence of ZFP in the flux profile of a component in a multi-component diffusion couple indicate that there are strong diffusional interactions or strong cross effects. This is also apparent from the development of uphill diffusion region here. So, for example, from point B to D, you can see the flux is negative. That is, in our convention, the component I is diffusing from right to left. So, if you see between D and B, the component is actually moving up its concentration gradient, and there is the uphill interdiffusion region developed for component A, developed for component I. This is again because of the strong diffusional interactions that can occur. Let us see how. So, we know the component the interdiffusion flux, let us say I is 1 here. In a ternary system, for example, J1 tilde is given by J1 tilde is equal to minus D11 tilde 3 dou C1 by dou x minus D12 tilde 3 dou C2 by dou x, and where the flux is 0, we have D11 tilde 3 dou C1 by dou x is equal to minus D12 tilde 3 dou C2 by dou x, which means the main term is equal to the cross term. This term characterizes the effect of component 2 on the diffusion flux of 1. The first term characterizes the effect of component 1 on its own diffusion flux, and here at the 0 flux plane the two effects are same. That means strong diffusional interactions exist in this region, and here in fact the component 1 is moving up its own gradient. So, the effect of cross term is more than the main term, and this is the significance of 0 flux planes and uphill diffusion region. We can also see if we look on either side of ZFP, on the left side diffusion flux is negative, that is component is moving from right to left. On the right side diffusion flux is positive, that is the component is moving from left to right. So, there is a reversal of flux on either side of the 0 flux plane or ZFP. Also, we know each composition plane is moving with time, right. We derived the expression for velocity of composition plane earlier, v of c I x over 2t, and so each composition plane is moving with time. So, zero flux plane is also moving with time. And what happens as the zero flux plane composition is moving, we can see in the volume swept by this ZFP there is a continuous reversal of the flux, where initially the flux was negative, after a certain time it will become positive. So, the component is changing direction of diffusion in the volume swept by the ZFP. These ZFPs are so very important when we are studying the diffusional interactions, and we want the diffusion couples which would develop ZFPs and uphill diffusion regions. Dayananda has studied such couples extensively by forming isoactivity couples. That means, a diffusion couple in which the thermodynamic activity of a component is same in both the terminal alloys to start with. In such couples, the zero flux planes are developed at a composition where the thermodynamic activity of that component is same as that in the two terminal alloys. So, this is how the nature of interdiffusion flux profiles look like. I will talk about this formula again. So far we integrated for the interdiffusion flux from left terminal alloys. Why not from right terminal alloys? In fact, we can integrate from any of the terminal, left or right, it should not matter. I will demonstrate how. So, again consider this concentration profile, Ci minus concentration in left terminal alloy, Ci plus concentration in the right terminal alloy, and suppose if we want to determine flux at point x, so if we integrate from right instead of left, what happens? If we write integral Ci plus to Ci at x, x minus x naught dCi, if we write in terms of areas, so let me assign some labels A, B, C, D, E, G. So, we can split this integral at the metano plane, the initial contact plane here. You can write Ci plus to x naught to Ci at x naught, x minus x naught dCi plus integral Ci at x naught to Ci at x, x minus x naught dCi. This integral is nothing but area ABC A, and the sign you are integrating from right, dCi is positive because as going from right to left Ci is increasing, and x minus x naught is also positive on the right side of the metano plane. So, this has a positive sign, and this integral is nothing but area CDE. Here now x minus x naught has changed its sign because it is now negative on the left side of the metano plane, but dCi is still positive. So, this has a negative sign, And the way we found metanoplane, we know this area ABC should be equal to area GCF. Right? That is how we found the metanoplane. So we can write this as area GCFC minus area CDEC. So this area minus this area is nothing but area GDEF. And area GDEF is nothing but integral Ci minus to Ci at x, x minus x naught dCi. So whether you integrate from left terminal or from right terminal, it should not matter. So we can modify the formula a little bit for Ji tilde at x as integral from either Ci minus or Ci plus to Ci at x, x minus x naught dCi. We need to multiply by 1 over 2t. Now once we find the interdiffusion flux, our next objective is to find the interdiffusion coefficients. And what is the method used for that, we will see in the next class.